Thanks a lot for the invitation. So I'll put my Intel's hat here and will represent Intel's Neuromorphic Computing Lab. I also have a new university position at the Zurich University of Applied Sciences, but here I'm now all Intel. I'm jumping it for Andreas Wild, who could only join remotely, and we thought a live participant might be better for you guys, even a heavily jet-lagged one. So I will talk about visual processing with Loihi 2. So I will present tools and systems that we have developed so far and are developing now for you to use Loihi 2 for visual processing. So I will skip all the motivation and trying to convince you that neuromorphic computing is great. I assume you all know that. I will also save you from just boasting about our results on Loihi 2. So it won't be about that. Just a quick update of where Neuromorphic Computing Lab stands now on tools and systems that you require for visual processing. That being said, for those of you who don't know Loihi, a couple words on what that is. So Loihi is a system, is a multi-core system that guarantees minimal data movement by tightly integrating compute and memory. So it's a multi-core system with a lot of memory associated with every core and with asynchronous processing in these cores. So it's a massively parallel system and supports event-driven computation and communication. We have systems that one can try out and use on a scale from edge computing to large-scale computing, like data center computing. And this device is now part of the event-based family, and we are now working on event-based vision applications that Loihi will support in the near future. And that's shown like in the second pane. So we have input-output exposed through Goldfinger connectors that will allow to use this system, Loihi system, for low latency applications. And we're also working on tight integration between event-based cameras and Loihi chip. And then hardware is of course great, but hardware is only as good as the software that is out there that enables users to use it. And Intel now invests a lot in developing software framework, software toolchain, with the core component called Lava. So that's the software framework that goes all the way from talking to the hardware, so having compiler and the runtime that supports different backends, CPU, GPU, and Loihi. Conceptually, we could support other neuromorphic platforms as well, but we of course will rely on the community developing compiler and all the low-level software to support different hardware systems. And then we have kind of the user interface, the API, Lava, that allows you, using high-level Python language, draft the networks that you would like to put on Loihi. And its framework is event-based, multi-paradigm, multi-abstraction, multi-platform, open source, importantly. The core element of this framework are processes. So we say everything is a process. The neuron is a process that runs over time, can communicate with other processes, other neurons. If you have a layer in your network, that will be a process. And you can combine multiple such layers in a large system that can run on heterogeneous platforms. So part of it can run on a CPU, some can run on a GPU, and some can run on Loihi, and they all communicate with each other in this event-based paradigm. And then we also develop a layer of libraries or algorithm libraries. So these are different frameworks with which you can configure neuromorphic hardware or Loihi in particular. And deep learning is one of these frameworks. We have another one for optimization workloads, another one for attractor dynamics or vector symbolic architectures, and more could come and be added to the list. So the systems that we offer now for users, the one system is called Kapoho Point. It's the credit size card type of a system with 8 chips on it. So there are 4 on one side and 4 on the other side. You can have networks with up to 8 million neurons, like almost 1 billion synapses. Supports different interfaces, and I'll talk a bit more about it in a second. The dimensions, like I can show it like this. So pretty compact system, and it's stackable. So you can expand it. It's scalable. Okay, so the system architecture. So this is the Loihi board. We interfaces with something we call host computer. It's a Cyclone V with ARM core processor, which mainly supports the gigabit Ethernet interface into Loihi. There also will be a 10 gigabit interface going directly into the chip. Right, so it looks like this. And then additionally to that, we have another board that is there to support direct interface to event-based cameras, to event-based sensors, with an FPGA just to make that efficient. So another view on the whole system. So Loihi can be configured using a host computer, host CPU, with all the system memory. You can use a number of interfaces, PCI, Ethernet, USB or MIPI, your favorite interface, to connect to different sensors. And we are now looking into standard RGB camera, RealSense, RGBD camera, a DVS camera. A DVS camera will additionally have a direct asynchronous hardware interface for low latency applications to Loihi accelerator. And then you can also have other accelerators in the overall system. We are currently working on an example application that puts together an RGBD camera and an event-based camera. So we're developing software to do pre-processing of both event stream and RGBD stream on the host computer. So we are now working on enabling the hardware support for fast input-output interface that will allow you to have really low latency applications on Loihi. And then on top of that, they have all these algorithms that can be, deep learning-based algorithms or other ones. So this under construction bit is the very important one. So I'm also waiting impatiently for it to be ready, and it officially will be released to our users and the community in Q3 this year. So how our partners and us use the Neuromorphic chip today for vision applications is in this pipeline. So most people still like to use deep learning because that has a clear framework and easy way to design algorithms. So here in the pipeline, you have a kind of one pipeline for training the network, and you can use different tools to do that. We use Slayer to train networks directly in SNN domain. You can train network as an artificial neural network and then transfer it into SNN domain. And then we have the interface using HDF5 files to kind of port your network on Loihi for inference. So the network will be expressed as these processes, lava processes, as I said. So each layer will be a process. You have your network, it will be compiled, put on a chip, and you can run your inference. So that's the pipeline that we have today. And today, most of the solutions, they use more or less conventional deep neural network architectures, CNNs, transformers, in their spiking version. Because we are on a neuromorphic hardware, then usually we won't be able to put your favorite very large language model on a chip. You have limitation with the number of neurons and number of synapses. So usually you would have some small scale networks, and you will target energy constrained, real-time embedded applications. So signal processing where you have some simple task, but you need to run it really fast on a really power restrained setup or scenario. And these are the examples. So RGB or DVS visual processing for scene analysis, object detection, navigation, the pilot network, so really a simple network, which you might want to run very, very efficiently. Audio processing, so there's this DNS challenge that Intel was running for denoising applications in a small form factor, or motion processing, so for optic flow detection and motion classification tasks. So this is what we have today. This is what most people do on a chip today. In the future, we would like to develop algorithms that go beyond just deep learning and develop algorithms that really exploit all the features of this asynchronous, massively parallel with fine-grained parallelism architecture. And one of the methods is training sparse models, so really exploiting sparsity that can be enabled on chip. Training recurrent models, because the spiking neural networks, their main feature is that you have this recurrency and statefulness of your computation inherent in the hardware. So instead of unfolding your recurrent network in time, you just train the recurrent network directly. Optimization is an important workload where we see large gains in computing time and power. And then we have this framework that supports designing optimization algorithms on Loihi. And it can be applied to all kind of logistics tasks, but also can be applied to, landmark extraction, pose estimation, SLAM, representing objects in graph-like networks on chip. And then designing algorithms that are kind of heterogeneous algorithms with different modules. For instance, with an attention module that is able to cut out part of your visual field and then do some computing only on this part with high resolution, but with a small part of the visual field, and then having an algorithm that can shift this attention window to different parts of your visual field. So here you not only have some kind of a deep network that does classification, but you also have an attention algorithm that is a different type of some recurrent neuronal network probably, and then you have some neuronal state machine that switches from one region to another one. Sorry, my voice is losing me. Yeah, so in the future, we aim to develop different types of algorithms that really exploit the properties of the hardware. So it will be efficient and smart, sensing at edge, low latency. In our language, it's workloads below 1 millisecond latency. Low power in our language is below 1 watt. Some might argue whether that's low enough. Improved efficiency with event cameras, exploiting the properties of event cameras like high dynamic range or little motion blur, multi-sensor support and support for heterogeneous networks, and importantly, ability to adapt to the networks on the chip using on-chip learning rules, right, that neuromorphic hardware and in particular Loihi support. All right, thanks a lot. I hope I am on time. Some other information.